Welcome to our deep dive into designing a real-time traffic monitoring system, a classic challenge often featured in Google system design interviews. Today, we'll explore the mechanisms and strategies behind building a robust solution that can handle streaming data, fuse information from multiple sources, and deliver accurate traffic states with low latency. We'll break down the problem, discuss the core domain model, and walk through the essential mechanisms that ensure correctness, scalability, and reliability. Whether you're preparing for an interview or curious about large-scale distributed systems, this journey will equip you with practical insights and best practices. At its core, a real-time traffic system is a streaming state estimation problem mapped over a road graph. Raw signals from loop sensors, cameras, and GPS devices arrive continuously, each with unique characteristics and timing. The system must normalize these signals, aggregate them into per-RoadSegment states, and serve this information with tight freshness bounds. Handling time, scale, correctness, and data fusion under imperfect inputs is crucial. This foundational understanding sets the stage for the mechanisms we'll discuss throughout the video. The domain model begins with the road graph and segmentation. Everything depends on a stable segment abstraction. Segments must be small enough for speed uniformity but large enough to avoid sparse data. Each road segment is a directed edge in the road graph, defined by geometry, length, speed limit, road class, and adjacency. This segmentation enables precise aggregation and analysis, forming the backbone of the traffic monitoring system. A compromise between spatial resolution and signal density is a key design consideration. Real-time serving, each segment maintains a compact current state record. This includes average speed, flow, density, congestion level, and freshness metadata such as last event time, last ingest time, and confidence score. The system also keeps a short horizon history to compute trends, detect anomalies, and avoid jitter. This approach ensures that each segment's traffic state is up-to-date, reliable, and ready for fast queries, forming the basis for analytics and route computation. Sensors report data on different clocks, cadences, and semantics. To build a robust pipeline, early normalization is essential. The system defines a single canonical event envelope, including event ID, source ID and type, event time, ingest time, location binding, measurement payload, and quality hints. Map matching for GPS data is critical, involving candidate generation, scoring, path consistency, and outputting segment IDs with confidence. Deduplication and idempotency mechanisms ensure that retries and duplicates do not corrupt aggregates. GPS data rarely comes labeled with a segment. The system must generate candidates for nearby road geometries, score them based on distance and heading, and ensure path consistency over time. This mechanism outputs segment IDs with confidence, avoiding systematic errors near overpasses, dense downtown grids, and parallel roads. Accurate map matching is vital for reliable traffic state estimation, especially in complex urban environments where precision matters most. Real-world systems encounter retries and duplicate events. To prevent aggregation drift, the ingestion layer uses event IDs to deduplicate incoming data. If event IDs are unreliable, a stable fingerprint is derived from source ID, event time bucket, and measurement sequence number. This ensures that state updates remain deterministic and aggregation is idempotent, maintaining correctness even under imperfect input conditions. Messages often arrive late and out of order. Aggregating by event time, not ingest time, is key to accurate traffic monitoring. The system maintains rolling window states for each segment, accepting late events up to a bounded lateness. After this bound, late events are treated as historical corrections. Incremental aggregates and robust statistics, such as median speed estimates and outlier counters, help maintain reliable segment states. Traffic data is noisy, with occasional spikes and inconsistencies. The system rejects physically impossible values and inconsistent jumps, such as abrupt changes from free flow to gridlock. Robust aggregation methods like median of samples or trimmed means are preferred over raw means when sample sizes allow. When samples are sparse, smoothing and priors are used to stabilize estimates, ensuring the reliability of traffic state data. Stable UI numbers are important, but algorithmic latency must be minimized. The system keeps an unsmoothed instantaneous estimate for internal detection and publishes a smoothed estimate blending new evidence with recent state. Smoothing is adaptive. High sample volume trusts new data more, while low volume relies on prior state. This mechanism avoids jitter on low signal segments and reacts quickly on busy roads, balancing stability and responsiveness. Traffic monitoring relies on multiple data sources, loop sensors, cameras, and GPS. Each has unique biases and limitations. Fusion is explicit and explainable, using weighted evidence based on historical reliability, current quality hints, and sample size. Conflicts between sources are handled by reducing confidence and avoiding repeated congestion level flips. Disagreement scores help flag sensor faults and mapping errors, ensuring robust segment-level estimate. Real-time queries require the latest per segment state, while analytics need historical time series. The hot store keeps current state records and a small recent history for each segment, enabling fast overwrites and reads. To scale, the system partitions by segment ID hash and stores values compactly in memory. The cold store is append only, retaining raw events or per-minute aggregates for auditing, trend analysis, and model improvements. Partitioning by time and region ensures efficient scanning. Finding nearby segments is a spatial index problem. The system precomputes mappings from spatial cells to segment IDs. At query time, it converts latitude, longitude, and radius into covering cells, fetches segment IDs, retrieves current states, and applies exact distance filters. This approach avoids expensive geoscans and makes query costs proportional to local density, ensuring fast and scalable spatial lookups. Route requests involve multi-key reads and reduction. For each segment, the system fetches current average speed and confidence. If a segment is stale, it falls back to the last known good window or historical typical speed, marking responses with lower confidence. Route computations avoid end-round trips by batching reads, co-locating serving layers, and compressing payloads. Consistency is ensured by reading with a target snapshot time, preventing mixed time results. Route results must be internally consistent, with all segment speeds from roughly the same time. The system reads with a target snapshot time, picking the latest fully published window and serving all segments from that boundary. This prevents mixed time results and ensures that route computations are reliable and accurate, even as data streams in continuously. Freshness is more than a timestamp. The system distinguishes between producer silence, pipeline delay, and disagreement. It exposes last event time, last update time, freshness seconds, and confidence scores. If freshness exceeds a threshold, congestion classification is frozen and confidence is degraded. For clients, marking data as unknown is preferable to confidently wrong estimates, ensuring transparency and reliability. When freshness seconds exceed a threshold, the system freezes congestion classification and degrades confidence. This prevents aggressive guessing and ensures that clients receive honest, transparent information. Marking data as unknown is often better than providing confidently wrong estimates, especially in critical traffic scenarios where reliability matters most. During bursts, such as network reconnects or outage recoveries, the system must avoid cascading failures. Ingestion accepts events quickly and persists them to a durable log, while processing consumes at its own pace. If backlog grows, the system prioritizes newest event time buckets for real-time state and may drop or downsample extremely old events. Per-source quotas prevent malfunctioning devices from flooding the system, ensuring reliability and stability. When the system faces overload, load-shedding mechanisms kick in. The system may drop or downsample old events from the real-time path, but retains them in cold storage for auditing and analysis. This strategy ensures that real-time processing remains responsive and avoids cascading failures, while historical data is preserved for future use. Security is paramount in traffic monitoring systems. Sensors and producers are authenticated as devices, not shared credentials. Mechanisms include device identity with rotating credentials, request signing, replay protection, and per-device authorization. Devices can only submit data for their allowed regions or segment IDs, ensuring data integrity and preventing unauthorized access. Public APIs must be protected with user authentication, rate limiting per key or IP, caching of common reads, and strict input validation. These measures absorb traffic spikes, prevent abuse, and ensure that only valid requests are processed. Input validation includes bounds on latitude, longitude, radius, and segment lists, safeguarding the system against malicious or erroneous inputs. Scale effectively, the system partitions event ingestion by segment ID or region, ensuring that all data for a segment is processed in order by the same worker. The state store shards by segment ID hash for even distribution, and spatial index shards by cell ID. This partitioning enables horizontal scaling, allowing stateless services to scale by adding instances and stateful components to scale by sharding. Stateless services, such as ingestion frontends and API servers, scale horizontally by adding instances. Stateful components, including stream processing state and hot store partitions, scale by sharding. This approach ensures that the system can handle increasing loads, maintain performance, and distribute updates evenly across the infrastructure. Protect against expensive nearby requests, the system caps radius, limits the maximum segments returned, and supports paging. Partial results are returned with clear metadata rather than timing out. This mechanism ensures that the system remains responsive and scalable, even under heavy query loads or large spatial requests. Who exactly once end-to-end processing is expensive, but effectively once is sufficient for traffic systems. Ingestion is at least once, with deduplication by event ID making aggregation idempotent. State updates are deterministic per segment and time bucket, ensuring correctness even under retries and duplicates. Crash recovery mechanisms replay from durable logs and reconstruct window states from checkpoints or recent history. If processing workers crash, they restart by replaying from the durable event log. Window state is reconstructed from persisted checkpoints or rebuilt from recent history. Since updates are idempotent, replays do not corrupt aggregates. This robust recovery mechanism ensures that the system maintains correctness and reliability, even during partial outages. During partial outages, the system serves from cache and marks data freshness explicitly. If ingestion is degraded, it keeps serving the last known state and increases staleness. If a region's sensors go dark, the system falls back to GPS-derived estimates and historical baselines with reduced confidence. These fallback mechanisms ensure continued operation and transparency during failures. Aggregating by event time with late data handling is a critical mechanism. This approach ensures that the system accurately reflects current traffic conditions, even as messages arrive late or out of order. By maintaining rolling window states and accepting late events within bounded lateness, the system avoids oscillations and mishandling of backfills, providing reliable traffic estimates. Making ingestion idempotent and handling duplicates explicitly is essential for correctness. The system deduplicates events using event IDs or stable fingerprints, ensuring that retries and duplicates do not corrupt aggregates. This mechanism maintains deterministic state updates and supports robust aggregation, even under imperfect input conditions. Separating hot, latest state storage from cold historical storage is a deliberate design choice. The hot store enables fast real-time queries, while the cold store retains historical data for auditing, trend analysis, and model improvements. This separation ensures that the system can serve both immediate and analytical needs efficiently, supporting a wide range of use cases. Building a spatial index for nearby queries, rather than geoscanning traffic rows, is a key mechanism. Pre-computing mappings from spatial cells to segment IDs enables fast lookups, reduces query costs, and scales efficiently with local density. This approach supports responsive spatial queries and avoids expensive operations over the entire dataset. Treating fusion as weighted evidence, with confidence and disagreement tracking, ensures robust segment-level estimates. Each source contributes an estimate with uncertainty, weighted by historical reliability, quality hints, and sample size. Disagreement scores flag sensor faults and mapping errors, preventing repeated congestion level flips and maintaining reliability. Freshness and confidence are exposed as first-class fields, not afterthoughts. The system provides last event time, last update time, freshness seconds, and confidence scores, enabling clients to make informed decisions. Transparent exposure of these fields ensures reliability and trust in the traffic monitoring system. A deliberate plan for backpressure and overload includes shedding and prioritization. The system prioritizes newest event time buckets for real-time state, drops or downsamples old events, and enforces per-source quotas. These mechanisms prevent cascading failures, maintain responsiveness, and ensure reliable operation under heavy loads. System design interviews often test your understanding of proximity and tri-concepts. In traffic monitoring, spatial indexing and efficient lookup mechanisms are crucial. By pre-computing spatial mappings and using tri-like structures, the system supports fast, scalable queries and robust aggregation, demonstrating mastery of distributed systems and data structures. Key takeaways for system design interviews include aggregating by event time, handling late data, making ingestion idempotent, separating hot and cold storage, building spatial indexes, treating fusion as weighted evidence, exposing freshness and confidence, and planning for backpressure and overload. Mastering these mechanisms demonstrates deep understanding and practical expertise in distributed systems. Designing a real-time traffic monitoring system involves distributed systems concepts such as partitioning, sharding, horizontal scaling, and failure recovery. Understanding these principles enables you to build scalable, reliable, and efficient solutions that can handle streaming data, fuse information from multiple sources, and deliver accurate traffic states under heavy loads. Best practices in software engineering for traffic monitoring systems include early normalization, robust aggregation, adaptive smoothing, explicit fusion, transparent freshness and confidence exposure, and deliberate backpressure handling. These practices ensure correctness, reliability, and scalability, forming the foundation for successful system design interviews and real-world implementations. Google system design interviews focus on your ability to handle time, scale, correctness, and data fusion under imperfect inputs, demonstrating mechanisms such as event-time aggregation, idempotent ingestion, spatial indexing, weighted fusion, freshness exposure, and overload handling showcases your expertise and readiness for large-scale distributed systems challenges. Reliability in distributed systems is achieved through mechanisms like durable event logs, checkpoint recovery, idempotent updates, and fallback strategies. These ensure that the system maintains correctness, recovers from crashes, and continues operation during partial outages, providing robust traffic monitoring even under challenging conditions. Tracking confidence and disagreement between data sources is essential for robust traffic state estimation. Weighted evidence fusion, quality hints, and disagreement scores help flag sensor faults and mapping errors, ensuring that segment-level estimates remain reliable and transparent, even when sources conflict. Spatial indexing mechanisms, such as pre-computing mappings from spatial cells to segment IDs, enable fast and scalable nearby queries. This approach reduces query costs, supports density-based scaling, and avoids expensive geoscans, forming a critical component of real-time traffic monitoring systems. Handling imperfect inputs, such as late messages, duplicates, and noisy data, is a core challenge in traffic monitoring systems. Mechanisms like event-time aggregation, deduplication, robust statistics, and adaptive smoothing ensure that the system maintains correctness and reliability, even under challenging conditions. In summary, designing a real-time traffic monitoring system involves streaming state estimation, robust domain modeling, event normalization, aggregation by event time, multi-source fusion, efficient serving paths, spatial indexing, security, scaling, failure handling, and best practices. Mastering these mechanisms prepares you for system design interviews and real-world distributed systems challenges. Thank you for joining this comprehensive walkthrough of designing a real-time traffic monitoring system for Google system design interviews. We've covered the essential mechanisms, best practices, and distributed systems concepts that underpin robust, scalable, and reliable solutions. Whether you're preparing for an interview or building real-world systems, these insights will guide you towards success. Stay tuned for more deep dives into system design and distributed engineering topics.